We chemists are often interested in knowing how much is consumed in a particular reaction or how much product is formed. Perhaps you want to calculate how much carbon dioxide is formed when a tank of gasoline or petrol is combusted. Or maybe you want to calculate the chemical formula for some substance. I'll show you how it's done. To learn this, let's start with the real classic: how hydrogen and oxygen react to form water. Let's start with just a word equation. Hydrogen gas plus oxygen gas turn into water. The chemical equation, I'm sure you've already seen it several times. 2 hydrogen molecules plus 1 oxygen molecule turn into 2 water molecules. What we're going to study in greater detail right now, that is why there are 2 hydrogen molecules that react and why 2 water molecules form. Take this to your notes too. Why is the chemical equation balanced? Stoichiometry. And take this down too, that stoichiometry, it's all about relative quantities in chemical reactions. I'll explain what I mean by that in a short while. But now let's see some animations, so just follow along and see what happens when hydrogen reacts with oxygen. First, we have a hydrogen molecule. In hydrogen gas, the atoms come 2 by 2, bound together like this. Why it is like this, I'll explain in my video about covalent bonding. For now, you just have to accept that this is just the way it is. Likewise, in oxygen gas, there are 2 oxygen atoms in each molecule. Now, when these two react, they form a water molecule and, what is this? A single oxygen atom? If you remember from the word equation we wrote earlier, only water is formed, not some single oxygen atom like this. This oxygen atom doesn't just disappear in some way. Instead, we must add another 2 hydrogen atoms like this, so we can see that water and nothing but water is formed. So, we now see that 2 water molecules form in this reaction. But these extra 2 hydrogen atoms, they don't just appear out of nowhere. They must have been there from the beginning too, which means that there must be 2 hydrogen molecules that react with 1 oxygen molecule. And they turn into 2 water molecules. Everything that is here on the left side of the reaction arrow turns into everything that is on the right side. Nothing suddenly disappears or appears out of nowhere. Everything is still there. So this is the balanced equation. 2H2 plus O2 turns into 2H2O. Now copy this and add this comment. The mass is conserved. Nothing disappears or appears out of nowhere in the reaction. So, what does this chemical equation tell us? Let's write it once again. 2H2 plus O2 turns into 2H2O. Well, it tells us that we need 2 hydrogen molecules and 1 oxygen molecule to form 2 water molecules. We can also put it this way, that we need twice as many hydrogen molecules as oxygen molecules for everything to turn into water. We can express this a bit mathematically with a quantity ratio or relative quantities as well. We say that the amount of hydrogen is related to the amount of oxygen and water as 2 to 1 to 2. Let's put that to use a little bit. We write a large, lovely table where we put the chemical equation in the table header in this way. What the chemical equation says is that if we have 2 molecules of hydrogen, they react with 1 molecule of oxygen. Together, they form 2 molecules of water. But the chemical equation also tells us, as I said, about the quantity ratio in the reaction. This means that if instead 2 pairs of hydrogen molecules react, it does so with 1 pair of oxygen molecules, and 2 pairs of water molecules are formed. We can do the same reasoning with dozen instead. If 2 dozen hydrogen molecules react, then 1 dozen of oxygen molecules are needed to form 2 dozen water molecules. But if we instead have 4 dozen hydrogen molecules, how many dozens of oxygen molecules do we need then? Well, the quantity ratio in the reaction tells us that the number of hydrogen molecules must be twice as large as the number of oxygen molecules. Therefore, we need half of 4, that is 2 dozen oxygen molecules. And the quantity ratio also tells us that the number of water molecules that are formed is exactly as large as the number of hydrogen molecules that react. Thus, 4 dozen water molecules are formed. Then we can of course use the unit mole as well. Mole is just a number, much like dozen or pairs. So if we have 2 moles of hydrogen molecules, 1 mole of oxygen molecules is needed for 2 moles of water molecules to form. But what do we do if, for example, we only have 1 mole of hydrogen? Well, the amount ratio in the reaction is still such that the number of hydrogen molecules must be twice as large as the number of oxygen molecules. If we only have 1 mole of hydrogen, we must have 0.5 moles of oxygen, and then 1 mole of water is formed. Now, for the last calculation, in this table at least, if we have 2.50 moles of hydrogen, how much oxygen is then required? Well, we need half of that, which is 1.25 moles of oxygen, and then 2.50 moles of water form. Let's do some mass calculations too. We look at the same reaction, 2H2 plus O2 turns into 2H2O. This time, let's say we have 1 mole of hydrogen gas which reacts with 0.5 moles of oxygen gas and forms 1 mole of water. Now, I'll use this equation to calculate the masses of everything that reacts. That is, the mass is equal to the molar mass times the amount of substance. The molar mass for hydrogen gas, H2, is 2.016 grams per mole. If we multiply by the amount of substance, 1 mole, we see that the hydrogen gas in this reaction weighs 2.016 grams. The molar mass for oxygen gas is 32.0 grams per mole, and multiplied by 0.5 mole, we get that the oxygen that reacts weighs 16.0 grams. Now, let's also look at how much 1 mole of water weighs. I can calculate that the molar mass of water is 18.016 grams per mole. And if we have exactly 1 mole of that, it weighs 18.016 grams. Let's fill in the masses down here in the table. Can you now see that the mass of the reactants is equal to 18.016 grams, exactly as much as the mass of the product, water? That's what we mean by conservation of mass. The mass in a chemical reaction is conserved. That is, the mass of the reactants is always equal to the mass of the products. Let's have a look at another example. We look at the combustion of methane, CH4, and what happens in that reaction. Before we can do any kind of calculation, we must consider a few things. What reacts and what forms. And then we'll have to write a chemical equation too. First off, what is it that reacts? Well, we have methane, CH4. And in a combustion reaction, it reacts with oxygen, O2. But what is formed? Well, when hydrocarbons, like methane, and carbohydrates, like sugar, are combusted, carbon dioxide and water always form. You write that down too. Now, let's write a word equation for that too. Methane plus oxygen gas turns into carbon dioxide and water. Now we can translate the words into chemical formulas. We have methane, we have oxygen, we have carbon dioxide, and we have water. Now the question is how many methane and oxygen molecules that react, and how many carbon dioxide and water molecules are formed. If you look at the chemical equation, you'll see that there are 4 hydrogen atoms in the methane molecule here. But to the right of the reaction arrow, you see that there are only 2 hydrogen atoms in this water molecule. Remember, the mass is conserved. No atoms disappear or form in the reaction. Therefore, we have to squeeze in a 2 here as a coefficient that tells us that 2 water molecules form in this reaction. Now we turn our attention to the oxygen atoms. To the right of the reaction arrow, there are 2 oxygen atoms in the carbon dioxide and another 2 in the 2 water molecules. All in all, 4 oxygen atoms. But to the left, there are only 2 oxygen atoms in the oxygen molecule. For this to add up, we must add some kind of coefficient in front of the oxygen gas too. I squeeze in another 2 in front of the oxygen here, so that I have 4 oxygen atoms to the left and 2 plus 2 oxygen atoms to the right as well. Let me show you a small animation also, so you can see more clearly what happens, what reacts and what forms. So we start with a methane molecule here and 2 oxygen molecules here. This is what 2O2 means, that we have two oxygen molecules. Now, watch closely as I do this animation and note that nothing disappears or appears. Every atom is still there after the reaction. One carbon dioxide molecule and two water molecules are formed. Now we can write down the relative quantities, which we'll use later. The amount of methane is related to the amount of oxygen gas, carbon dioxide, and water as 1 to 2 to 1 to 2. Time for another table. In the head, we write the chemical equation as before. CH4 plus 2O2 turns into CO2 plus 2H2O. And if we have a single methane molecule, this means that it reacts with two oxygen molecules to form one carbon dioxide molecule and two water molecules. If we do the same operation as we did with hydrogen, oxygen, and water earlier, we can see that if we have a pair of methane molecules, then we need two pairs of oxygen molecules to form one pair of carbon dioxide molecules and two pairs of water molecules. And of course, if we have a dozen methane molecules, we need 2 dozen oxygen molecules to form 1 dozen of carbon dioxide molecules and 2 dozen of water molecules. Let's use our favorite unit mole 2, that is 6.022 times 10 to the 23 methane molecules. If we have 1 mole of methane molecules, we need 2 moles of oxygen molecules, and then 1 mole of carbon dioxide and 2 moles of water molecules are formed. Now, what happens if we, for example, have 3.45 moles of methane? Well, the relative quantities tell us that the amount of oxygen must be twice as large as the amount of methane. Thus, we need 6.90 moles of oxygen gas. How much carbon dioxide is then formed? Well, the relative quantities tell us that the amount of carbon dioxide that forms is equal to the amount of methane, which is 3.45 mole. And the amount of water is also twice as large, that is 6.90 mole. Let's do a small calculation of that too. We write the chemical equation in the table head again, and then we'll calculate what happens when a mole of methane reacts with 2 moles of oxygen. I once again use this relation that the mass is equal to the molar mass times the amount of substance to calculate the different masses in the reaction. With help of the molar masses in the periodic table, I calculate the molar masses of the reactants. The molar mass of methane is 16 grams per mole, and multiplied by the amount of substance 1 mole, we get that 16 grams of methane reacts. The molar mass of oxygen gas is 32 grams per mole. This time, I have that 2 moles of oxygen molecules react, so the total mass of oxygen that reacts is 64 grams. Let's also look at the carbon dioxide. With help from the molar masses in the periodic table, I calculate the molar mass of carbon dioxide to 44 grams per mole. Since 1 mole of carbon dioxide is formed, the total mass of the carbon dioxide becomes 44 grams per mole times 1 mole equals 44 grams. Considering the water, the molar mass is 18 grams per mole. Since 2 moles of water are formed, I multiply 18 grams per mole with 2 mole and get that 36 grams of water is formed. Let's write the masses down here and we'll compare them to each other. Can you see here that the mass of the reactants is 80 grams and the mass of the products is also 80 grams? As you can see, the mass is conserved in the reaction. No atoms disappear or appear during the reaction. With this take-home message, I end the lesson. Don't forget that you can learn more and check your learning on my homepage. Links are in the description.